welcome to the third part of the Z procedure activity, Lab 6. Recall that in Part A, we examined the three assumptions of the Z procedure. The data are independent, they come from a normally distributed population, and we know the population variance. Under those circumstances, the distribution of the p-values from the Z-test, they're uniform 0, 1, which is what we would expect. The rejection rate is alpha, or close enough because of the randomness, which is what we would expect. In Part B, we violated one of those three assumptions. We violated the assumption of normality. The data came from non-normal distributions. And under those circumstances, we also examined the p-values, or the distribution of the p-values from the z-test, and those rejection rates. We discovered that if n gets large enough, then the distribution of p-values is going to be close enough to uniform 0, 1, and the rejection rate is going to be close enough to alpha. In this part of the lab activity, Part C, we're going to violate one of the other assumptions. We're going to violate the assumption that the population variance is known. And we're going to then look at the distribution of the p-values that come from that z-test. And we're going to look at the rejection rates. And we're going to discover that we need much larger sample sizes if we don't know the population variance. N equals 30 or 50 isn't going to cut it most of the time. You're going to need on the order of several hundred. And that's the purpose of Part C, is to show you that different assumptions have different levels of importance. So let's get started. And here we are in the third part to Lab 6. In the first part, we violated no assumptions of the z-test, did simulation, calculated 10,000 p-values, and looked at the distribution of those p-values, and looked at the observed rejection rate. We saw that the p-values had a uniform 0, 1 distribution, and the rejection rate was alpha or really close to alpha. In other words, if the assumptions are met, the test is appropriate. The z-test is appropriate. In Part B, we violated one of those assumptions. We violated, according to our list, assumption of normality. We used an exponential distribution with a rate parameter lambda equal to 1/2, and we tried 3 different sample sizes just to show you that with that distribution, the z-test still can be used, but the sample size has to be large enough. If the sample size is 5, z-test is wholly inappropriate. The rejection rate's smaller than alpha. The Kolmogorov-Smirnov test tells us that the p-values are not uniformly distributed. But when the sample size was 50, the rejection rate was really close to alpha. I think it rounded to 0.05. And the Kolmogorov-Smirnov test had a p-value that was greater than alpha, so we failed to reject the null hypothesis of uniformity. In this part of the lab activity, we're going to violate the third assumption, and that's the assumption that we know the standard deviation. We're going to calculate the standard deviation from the sample, and we're going to use that. I mean, that pretty much makes sense. If you don't know the population standard deviation, why don't you use the sample standard deviation? Yeah, let's see if that works. Let's see if we're able to use that test. So we're going to do the same steps as before. The following code assumes that we know the population standard deviation. Let's hop over to R. Again, this should look familiar. Line 3, we're creating our uniform, normal distribution, normal data. Sample size of 50. We're specifying that the mean is 2 and the standard deviation is 1. So we're going to use a z-test on that data. We're specifying, because somehow we know the population standard deviation in this case is 1. Somehow we know sigma. And then we're testing this under the null hypothesis. And the null hypothesis is that the average is 2. The average is 2. We ran this back in Part A, got p-values that were uniformly distributed. The change we're going to make here is no longer are we going to specify what the standard deviation is. We're going to calculate it on the fly. We're going to calculate it from the data. Remember, the function to calculate standard deviation is just SD. So the standard deviation of x will be SD parenthesis x and parenthesis. Put it in there, and that's the only change we're making. But it's an important change. Now we'll run this and we'll get an error. Could not find function z-test. Because I'm starting a new script, started a new session of R, therefore I have to have R import that z-test function. Same way as we did before, sourcing it, spelling things correctly. And I didn't spell things correctly. Oh, I see. 2 backslashes. There. Notice I got errors on the left telling me I did something wrong. Specifically, could not open file, which told me I had something typed incorrectly. So I went through and had to figure out what I typed wrong. But I ran it, gave me no error, so now I know that the z-test exists. In fact, if I want to see the code for the z-test, I'm going to type the z.test over here in the console window and hit enter. And there's the code for it. If you're interested in looking at the internals of how things work, this is one way of doing it. It also gives a nice little summary of what the function does. If you don't care about seeing the inside, seeing the guts, then you can just go ahead and ignore that. Now that the z-test function is loaded, we can highlight, Control R or Command Enter depending on what computer you're using. About a second later, we've got our p-values. And again, if we type p over in the console window and hit enter, we get all the p-values. We can look at a histogram of those p-values, see what that looks like. Control R. Yeah, I don't see anything. Could be wrong, but don't really see much. The rejection rate, remember we reject when the p is less than alpha, and the rate will just be the average of those. So the rejection rate is 0.0537. 10,000 is 100 to the power of 2, so we go to 2 decimal places and round it. So that comes out to be 0.05, which is alpha, so this is looking good. And then we can do the Kolmogorov-Smirnov test of p unif, and that's a comma. Control R, we get a p-value of 0.2329, which means there's no evidence that this is a bad test at this sample size. And I do again need to emphasize at this sample size. Because if we change the sample size, make it smaller, the test may become inappropriate. So this part we did with a sample size of 50. We're going to scroll down. Part 3, we're going to do it with a sample size of 30. Because a lot of books say if n is greater than 30, you're good to use the z-test. So what changes? I'm going to sit here for a moment, wait for you to look back over your code and figure out, what is going to change? What is going to change? What is going to, yeah, you're going to change the sample size. That gets changed to 30. Rerun. About a second and a half later. Histogram of those p-values. Okay, there I'm starting to see that it's not uniform. It looks as though that first bar is too high. Looks like it's uniform for most of it, but then starts to go up. But again, hey, it could just be from the randomness. I mean, we are only using 10,000 iterations. If we did it with 1,000,000, it would be much easier to see any patterns. The rejection rate, I'll go ahead and close that. The rejection rate is 0.0598. Ooh, that's high. And again, rounding it to 2 places, that comes out to be 0.06. So if we're using a sample size of only 30, we're rejecting true null hypotheses 20% more often than we should. Because we should be rejecting 5% of the time, but we're really rejecting 6% of the time. So that's an increase of 20%. That's not a good thing. And the Kolmogorov-Smirnov test gives us a p-value of 0.06448. That tells us that maybe that 6% rejection rate that we found, or 0.0598, Maybe that's just the randomness in reality. How could we tell? Well, reality is random, so that just means we got to keep doing this over and over and over again. So we'll rerun this. Sample size of 30 still. Control R. I mean, it only takes a second or so. Look at the rejection rate. It's 0.0591. It looks like it's consistently about 0.06. Kolmogorov-Smirnov test here, it's below alpha. So for this run, I'd reject the hypothesis that the test is appropriate. So we got one reject and one failed reject. Yeah, got to do it 3 times. Can't end on a tie. Rejection rate, 0.0621. It looks like it is hovering around 6%. Kolmogorov-Smirnov test, 0.03302. Okay, that's pretty low. That's also less than alpha. So that's 2 fails and that's 2 rejects and 1 failed reject. So it looks like 30 is right there on the bubble. I mean, you might be able to get away with 30. Maybe you won't get away with 30. 30, yes, 30, no. I'd say since we know a better test, and since we're getting that better test in class, I wouldn't use the z-test, but if I was on a desert island and all I had was a z-table, I think I would take the chance and use the z-test with the sample size of 30. Step 4, we're going to do it with the sample size of 100. Is a z-test still allowable? Change that to 100. Rerun. Took a little bit longer because you're getting 100 random variables each time through. Rejection rate of 0.054. Yeah, that rounds to 0.05. Kolmogorov-Smirnov test gives a p-value 0.3755. It's safely above alpha. But just to be safe, let's go ahead and rerun that and see what's going on. Still get a rejection rate that rounds to 0.05, but it does look to be a little bit high. In the first run, it was 0.054. In the second run, it's 0.0542. So it looks like it might be 0.054. Kolmogorov-Smirnov test still not able to detect a difference between the distribution p-values and the uniform distribution. So 100 looks like we're safe-ish. Notice here, when using a million iterations, the p-value for the Kolmogorov-Smirnov test will usually be less than alpha. Now I'm going to change the number of iterations to 1,000,000. So I'm going to change that from 1 times 10 to the 4th to 1 times 10 to the 6th. So you can just see how much the p-values smooth out. In fact, let's go ahead and put the histogram of the p-values with just 10,000 iterations. Actually, let's go ahead and keep that at 4 for a second and change this to 10, sample size of 10. Rerun that. Histogram looks like that. It's a little bumpy. Now, let's do 1,000,000 iterations. So 1,000,000 is 100 times more than 10 to the 4th. 10 to the 4th took about a second and a half. So a second and a half times 100, it was 150 seconds. So about 2.5 minutes for my computer to run these 1,000,000. So I'm going to run these. Control R. And we're back. Well, I hit pause and then came back later and then restarted it. But took 1,000,000, that was 1,000,000. We're going to get much more precise estimates, which means we're going to be able to do a much better job of determining if this is an appropriate test or if this is not. Refer back to the discussion on power. So finished up, here's the rejection rate. 0.0818, that's incredibly large. And here's the Kolmogorov-Smirnov test results. P-value is less than 2.2 times 10 to the negative 16th. So extremely small p-value, which means almost no evidence in favor of the null hypothesis that the test is appropriate, therefore test not appropriate. Sometimes you'll get this warning message, especially when you do a lot of simulations. one of the assumptions of the Kolmogorov-Smirnov test is that the two distributions are continuous. If they're continuous, then the probability of a tie is 0. But the reality is that when you do this over and over and over again, you're going to get a lot of ties because it rounds to 6 decimal places. So that's a warning that you can also safely ignore. And so this is the one I got when I did it last time, when I was putting the lab together. Notice the blue line is the uniform 0, 1 line, and it does look like that first bar, which is of width alpha, so that height should also be alpha under a perfect test. Looks like you're rejecting a little bit too much. And so this was the third part of the 6th laboratory activity. Here we show that the z-test really does depend on knowing the population standard deviation. If you don't know the population standard deviation, just using the sample standard deviation isn't going to cut it. At least not when you're using the z-test. You do need a sample size of at least 100 in order for it to be close to usable. Now, we really don't have to worry about knowing the population standard deviation because we've got the t-test, which we're learning about in class, where you don't need to know the population standard deviation. So if you don't know it, there's no reason to use the z-test. In fact, that's why I'm sure 1 or 2 statistical packages have it, but the vast majority of the statistical packages out there don't even have a z-test. It's because it's never usable in real life. And you can use a much better test, the t-test, in real life. So that's the end of this entire laboratory activity. Don't forget to do part Q, which is the homework part. If you have any questions, don't hesitate to ask, and I will see you in class.